All right. So we're going to move on now to sort of applying Newton's laws. Remember, this was a section in class where we did all the inclined planes and force problems, the elevators, all that jazz. So we're going to do some of that today. First, let's just sort of define some forces. And the first one is the frictional forces. By the way, I have a microphone today, so I'll post these online if you want to use them. I'm not sure how useful they'll be for you. But frictional forces. We have two types of frictional forces. That's static friction. That's Fs. And then we have kinetic friction. Fk. And static friction, of course, is not moving. Kinetic friction is when the two surfaces are moving with respect to one another. So, for example, if my car is rolling, the tires are rolling, what kind of friction is that? That's static friction, because the surface of the tire is static relative to the ground. They're not sliding across one another. But if you lock up your tires slide across the ground, and that would be kinetic friction. Generally, almost always the case is that static friction is bigger than kinetic friction for two materials. And you see this like when you're pushing something across the floor, it's more difficult to get it moving. Or when your tires lock up in your car, you start sliding across the road, whereas you wouldn't do that if your tires were rolling. Okay, we talked about in class how that's the idea behind what system in a car. Do you recall? Hey, very anti-lock brakes. So that keeps that static friction engaged so that kinetic friction doesn't come into play. And both of these can be found in this way. The static friction is said to be greater than or equal to the coefficient of static friction, mu s, times the normal force. And then kinetic friction is equal to mu k times the normal force. The reason for this inequality right here is that if I'm pushing on something, due to Newton's third law, the object is pushing back on me with the same force. So I push on it with 5 newtons, I push on it with 10 newtons, and then I push on it with 12 newtons, and I get it to move. 12 newtons is the maximum static frictional force. But the static frictional force can be anywhere between the maximum and 0, right, depending upon what sort of force is pushing on it. So the static frictional force is actually an inequality. The coefficient and then the normal force. If you think about this, if I have something that slides across the table, like if I push this, there's a certain amount of friction. But if I push down on it, what am I doing to the normal force? I'm increasing it. So now when I push it, look, it's a lot harder to move. It's not directly because I'm pushing down. Like the normal force isn't keeping it from moving. It's actually the frictional force. So by pushing it down and increasing the normal force, I increase the frictional force, and then it's hard for me to move in this direction. Follow me? By pushing down, increasing the normal force, I increase the frictional force. All right. They give this relationship. I don't know how useful it is, but they give this relationship. I'm going to give it to you here, but that mu s is equal to the tangent of the angle alpha, where if I have an inclined plane like this is my angle alpha, and this is my object, where the angle alpha is the angle where it first starts to move. So if I increase this to a certain angle until this block starts to move, whatever that angle is, the tangent of it is my coefficient of static friction. I don't know if that would come up. I haven't seen it in any of the problems that I've done, but they give that relationship, so it probably does come up at some point. All right. Yeah. No, so if I have this, imagine I have this block on this inclined plane, and I raise it up. At some point, my angle is going to get big enough so that this thing slides down, right? And it's at that point where the tangent of that angle is equal to the coefficient of static friction. Tried these before. They're really good, aren't they? Yeah. Is that clear, Alex? Okay. All right. Let's do some inclined planes. or first of all, we haven't said this outright, but the weight of an object, I think y'all all know this, is equal to m times g, where g is just the acceleration due to gravity, or 10 meters per second squared. We use 9.8, but I think since you're doing multiple choice questions, just keep your numbers really even. That'll help you in doing the calculations. And then you can pick the right answer from the ones that are given. Okay? Let's just do a simple problem. So let's say that we have a block like this. Let's say that this angle is equal to theta. I have a block. Let's say that my mass is 1 kilogram. Say that this angle is 30 degrees, and I want to know what is its acceleration. All right. I want to go through and I want to label all my forces. I have my normal force. The normal force, if you recall, we haven't said this, but the normal force is perpendicular to the surface. If I'm not on an inclined plane, it's easy, right? Like if I push down on this table with 10 newtons, I get an equal and opposite force by Newton's which law? Third law. I get an equal and opposite force that pushes back up on me. So that normal force is equal but opposite to the forces in the opposite direction. We'll see that in just a second. I get a weight that is in this direction. In this case, that weight is going to equal 1 kilogram times 10 newtons. Or excuse me, times 10 meters per second squared. So that's going to equal to 10 newtons. And then I'm also going to get my static frictional force. Notice that the static frictional force, or all frictional forces actually, are in the same direction or opposed to the direction of motion. They're opposite the direction of motion. So this block would tend to move down the inclined plane, so the frictional force is going to be up the inclined plane. All right, now I can draw a coordinate system. If this angle is 60 degrees, this angle is 30 degrees, and so this angle will equal to 60 degrees. So if I draw my coordinate system over here, redrawing all the vectors, I have Fn, Fs, and Fw. And Fw is at 90 minus theta. All right, 90 minus theta, which in this case is 90 minus 30, or 60 degrees. I think that's probably the easiest way to do it, because you remember your x and y components as the x is sine or cosine. It's cosine, and the y component is the sine or tangent. It's the sine, yeah. Okay, so I think it's easier to do your angles like this with the inclined plane. All right, let's, now we want to resolve our vectors into its x and y components. This is a basic 2D force problem, but I've seen a number of these in the practice test. So this is just what we want to do. We want to draw our forces that are on the axes, and now we want to take that weight and break it into its xy components. That's going to be Fw cosine of 60 and Fw sine of 60. All right. Then we apply Newton's second law. Remember, Newton's second law says the sum of the forces equals ma, and we'll apply that in both the x and the y directions. Sum of the forces equals in the x direction equals max. The sum of the forces in the y direction equals may. In most of these situations, one of these accelerations is going to be 0. Which is it for this one? The x or the y is going to be 0. Right, it's not accelerating in the y direction. And the reason it's not is because of the way we drew our coordinate system, which was rather clever of you to draw your coordinate system this way, because in drawing it this way with the inclined plane, one of your axes is not accelerating. That would not be the case, by the way, if you drew your coordinate system like this, with the x-axis here and the y-axis here. This y acceleration would be non-zero. It'd be some component of the total acceleration. So whenever you're doing your inclined plane problems, you always want to draw your coordinates like that. That's the way we do it. That's every book says do it that way. All right. So we can take this. Sum of the forces in the x is going to be Fs minus Fw cosine theta. Cosine 60, rather. That's going to equal max. And then over here, I get Fn minus Fw sine 60 equals 0. You're probably not going to have time to go through all these steps on an inclined plane problem to draw out all the vectors and stuff. So you might just want to, look back at this and try to memorize sort of the basic ideas behind inclined plane problems, because they seem to come up a lot. They're a common physics problem, and they exercise a lot of good concepts like vectors and forces and all that jazz. Okay, so let's see. We want to know the acceleration of the block. That is this acceleration. Something I didn't give you is the coefficient of static friction. Let's say that coefficient, rather, of kinetic friction is equal to, make it small enough, make sure we get something. I'm going to say that it's equal to 0.01. All right? Yeah, that should work. Okay, y'all with me on this? Is this jogging your memory? It's easy? Not easy? Some? Okay. So I want to know this acceleration. Look, I don't know the static friction, so I'll need to figure that out. So in order to find the static friction, I know that the static friction is equal to, or excuse me, we're going to call this kinetic friction, sorry, because we're assuming that it's going down the inclined plane. All right, so I'm going to call this kinetic friction, because I'm asked for an acceleration. So my kinetic friction is equal to mu k times the normal force. So in order to find this, I need to know what is the normal force. So I know that my normal force from here is equal to Fw sine 60. And this is where you pull out your memory sheet, because I don't remember mine either. Sine of 60 is root 3 over 2. So that's going to be 10 newtons times root 3 over 2, which is, what, 5 times 1.7, so that's roughly 5, what is that, 5 times 1.7. What is it? It's 8.5, yeah. 8.5 newtons. So that's my normal force. If this is 1.7, 5 times 1.7 is 5 times 1 plus 5 times 0.7. That's 5 plus 3.5, which is 8.5. All right, so that's our normal force. Now that we know our normal force, we can plug it in back here and find out what our kinetic friction is. And so our kinetic friction is going to equal 0.01 times 8.5 newtons. That's just moving my decimal place over twice, so it's going to be 0.085 newtons. That's my kinetic friction. You might just round that off to 0.1 at this point, all right? But I'll keep it like that for now. And now I just want to know what is my acceleration. So let's go back up to that other equation right here. Now that I have my kinetic friction, I have my weight. I can find my, my acceleration fairly easily. The acceleration in the x direction is going to equal Fk minus Fw cosine 60 divided by m, which is 0.085 minus, what was the weight, 10 newtons. Cosine of 60 is a half, divided by my mass, which was 1 kilogram, and that's going to be 0.085 minus 5, which is negative 4.015. Is that right? No, it's 4. What is it? Like 4.9. 4.915, right? Y'all are helping me out. Is that right? Yeah, 4.915. Negative 4.915 meters per second squared. All right. Let's look at a few questions. few practice questions for you. Not all of them are calculations. Some of them are you just look at an inclined plane and you have to give certain expressions or what have you. So, can I take this away for now? Okay. All right. By the way, these questions that I'm asking, I'm going to pull some longer passage questions, and we'll hopefully look at some today. But these questions that we're asking in class with our clickers, that'll be good. I mean, they're not going to be exactly like these on the exam, but it'll be good and a good indicator of what you'll see on the exam in here. Let me get my notebook. Let's just start out with a few simple ones. Just sort of about Newton's laws. Let's look at number 144. Well, they give you Newton's laws there. Which of the following is a violation of Newton's first law? It's number 144. Can y'all see that okay? I can see it? Yep. Which of these is a violation of Newton's first law? Y'all can't see that, can you? Let me zoom in a little more. How many do we have here today? 4, 8, 12, 18. Who? Oh, Josh. What'd you call him? See, y'all never tell me this. Oh, I'm not gonna do that. He doesn't want me to call him that. All right, 18. All right, just a few more seconds. All right. Very good. C is the right answer. C is very much an Aristotelian view of things. The Aristotelian view, if y'all recall, was Aristotle said that everything in a natural state, and that state is to be at rest, and that if anything's moving, it wants to get back to rest. All right. Let's look at number 47. Again, these are pretty simple, but let's just try this out. Just a bit longer. Stop at 130. A is right. They give some extra information here that's not really needed. What's not needed? The velocity is not needed. It's just asking for the acceleration. So by Newton's second law, it's just F equals ma. So A equals F over m. Let's try some more difficult ones then. So it's 10 over 5, which would be 2 meters per second squared. Let's look at number 184. We might come back to some of the others, but I think y'all are probably okay with much of these. Am I right? These simple ones. Let's try 184, which has to do with an inclined plane in particular. All right, so I have this frictionless inclined plane. H is the height of the ramp, b is the total length of the ramp, and theta is the angle from the horizontal. Given those values, how long does it take the mass to move the distance d? Good practice. I have a lot of the same stuff that we did in the previous one. Find the acceleration, find the distance it moves, and then use your kinematics equations to find the time. Or 20 more seconds. So we'll go on to 4 minutes. Stop at 4 minutes. Oh goodness, we're all over the board here. All right, let's see. So the first thing we want to do is we just want to find the acceleration, and then once we find that acceleration, we can use our kinematics equations. This one in particular, that x is equal to 1/2 at squared. Once we find that acceleration in the x direction, then we can find our time. So just like we did before, I'm going to draw my forces. I have my force weight, I have my normal force, and here it says it's frictionless, so there are no frictional forces. This is my axis. Now this angle is 30 degrees right here, so this angle is going to be what? 60, right? 90 minus 30. So the force along the x direction, the sum of the forces in the x direction, is just going to be Fw times cosine of 60. That's a good thing to remember, that if you have no other forces, that the component of the weight that's down the inclined plane is the x component. All right, because we draw our x-axis along the inclined plane. Yeah. Okay. So I have these things. Let's see. The mass is 2 kilograms, so that's going to be 20 newtons times the cosine of 60, which is 1/2. And so my force acting down the x-axis is just 10 newtons. Then I can find my acceleration. My acceleration equals F over m. That's going to be 10 newtons over, wasn't it 2 kilograms? That's going to be 5 meters per second squared. So this block is accelerating down the inclined plane at 5 meters per second squared. And then I can go back to this. Let's see, x isn't, or rather d, they call it, isn't given, is it? No, they give the height. So if I have a triangle like this, where this is 5 meters, and I want to know this distance, and I know this angle is 30 degrees, which function will I use to find d? The sine. So I say sine of 30 equals opposite over hypotenuse. Remember SOHCAHTOA, S-O-H. Sine of 30 is 5 over d. And then solve that for d. 5 over sine of 30 is equal to 10 meters. All right, so the length of that inclined plane is 10 meters. And now we have what is it? Have a mistake? Yeah. Oh, you had a mistake. Okay. And then so my distance is 10 meters. I'm plugging into this up here now. Remember, this had a couple other terms, which I'm leaving off. It had that x naught term, which I take to be 0, and it also had a v naught t term. But my initial velocity is 0 because it's initially at rest. Does it say that? Yeah, the mass starts from rest. But if that wasn't the case, you'd have to include that. So I have 10 meters equals 1/2 of the acceleration, which we found right here. It's 5 meters per second squared times t squared. And so I get 20 over 5. Oh, look, this is really nice. So is equal to t squared, so that's equal to 2. The root of 4 is 2. All right? That's not an easy problem. There are lots of steps that you have to do. You could be made a little bit easier, like you wouldn't have to draw all this stuff if you just remembered that the weight, the component of the weight, is the x component of the weight. And that's just going to be Fw times the cosine of 90 minus this angle. That's a useful piece of information to remember anyway, right? Like, just sort of use that all around, I think. It's useful, actually, to review these vector problems and remember these 2D force vectors, how they break down. Anthony? No, not always. Yeah, so it's quite a bit more complicated if it's not frictionless. Let's see if I picked out one.
I remember like one of the practice problems we kind of did in the book. It was like an incline friction problem with that, but there was like a block connected to another block with a row.
We're going to get some stuff like that, yeah, like a two-body problem. All right, so here the answer was C, right? Is that right? B, is that what you said? It was C, yeah. Good job, the 5 of you, whoever they were. Would y'all like to stand up now? The 5 of you that got it right? Oh, you were guessing, okay. Okay, let's see if I had a two-body problem I'd picked out. I can do a quick two-body problem. Is that okay? I don't see one right off in the problems that I picked. Well, let's do one real quickly. And then we're going to move on to circular motion, okay? We're moving really quickly through this stuff, but I want y'all to get as much as you can. Is that okay with y'all? All right, let me grab something right quick. Sometimes I have seen problems like this. Let's say you have these two body problems. Let's say that I have an inclined plane that looks like this, and then I have blocks on them. I'm going to do them without friction just to make it a little simpler. I have blocks that look like this. Let's say that this is a 2 kilogram block, and this is a 1 kilogram block. And let's say that this angle is 30 degrees. And I want to know just what is the acceleration of the whole system. Whenever you have two body problems, gosh, I don't think we did a whole lot of two body problems in the class, but they work exactly the same as other two body problems. I mean, as one body problems, except you just got two free body diagrams. So it's going to look like this. I'll just draw my force vectors on this body. This is going to be my tension force, and there's my weight. I'm going to call it FW2, meaning like 2 kilogram. And then I do a similar thing over here. I have my normal force, just drawing all my vectors. I have FW1, and then I have the tension force. And the thing here is that this tension is equal to this tension. You talked about this in your book. That when you have tension in a rope or whatever, that tension is felt all the way throughout the rope. And we did talk about that in 101. So if I pull on a rope on one end with 200 newtons, I'm going to feel 200 newtons on the other end of the rope. And so that's what I have here. Whatever tension I have in the rope on this 2 kilogram mass, I also have it in the 1 kilogram mass. Now, then we can do just like we did before, where I draw my x and y axes, this angle being 60 degrees, and draw this over here, my normal force, my tension, and I'm going to go ahead and do my x and y components, FW1 cosine of 60 and FW1 sine of 60. All right, now I can figure out some stuff. I can say that Ft, I can write my Newton's laws, apply Newton's second law. I can say Ft minus Fw2 is equal to m2 times a in the y direction. What's important on these two body problems is that you keep them separate. So here, this is the equation from Newton's second law. The sum of the forces equals ma, where this is my 2 kilogram mass. So be careful that you don't get your masses mixed up. That's a really common mistake, that I would put an M1 here, 1 kilogram, instead of the 2 kilogram. All right, so you're going to write two separate sets of equations, and that's for the 2 kilogram block. We could put in friction. That would be fine, but I just said let's just make this a simpler one. But yeah, you could say that there is friction, in which case if there was friction, you would have a force acting along this axis. That would be your frictional force.
So how would we know if we had friction when we're looking at like this one or considering friction?
It would tell you either there's friction or there's not friction. Like in the previous problem, it said that it was frictionless. All right? Okay, so then you want to write your equations for a second set of equations. So I like to just write them all out. So I say the sum of the forces in the x direction is Fw1 cosine of 60 minus Ft equals m1a. And then the sum of the forces in the y direction is Fn minus Fw1 sine of 60. And that's equal to what? It's equal to 0 because it's not accelerating in the y direction. This problem is pretty simple because we don't have friction. But if we had friction, like if it just gave the coefficient of static friction, then you'd have to solve this for the normal force and then find the kinetic frictional force, like we did in that previous problem. Okay? But here I'm just looking for the acceleration. Let's see, over here, I know FW2 and M2, but I don't know the acceleration, and I don't know FT. How is this acceleration going to differ from this acceleration? Is it going to be bigger, smaller, or the same? It's going to be the same, right? They're attached to a rope. We assume it doesn't stretch. So however one accelerates, the other will accelerate. And so that makes this problem kind of nice because these are common variables, but both of these equations have two unknowns, so you have to solve them both for those unknowns. So let's put in what we know here. On this one, I have Ft minus 20 newtons equals 2 times AY. And over here, looking at the sum of the forces in the x direction, I have 10 times cosine of 60, which is 5. That's 10 newtons. Where am I? Right here. 1 kilogram times 10 meters per second squared is 10 times cosine of 60, which is a half, so that's 5 minus Ft equals A. So look, now I have two equations with two unknowns. I can solve those. I like to do it by substitution. So I'm just going to take this and plug it in right here. So I say 5 minus, or excuse me, not there. Plug that, which is equal to A, right there. I get Ft minus 20 equals 2 times 5 minus Ft. And I just solve that for Ft. Get my glassy look over there. Is this okay? Okay, so Ft minus 20 equals 10 minus 2Ft. And solving this, I bring my 2Ft over. I get 3Ft equals 20 plus 10, which is 30. So my tension force is equal to 10 newtons. And then if I want to know my acceleration, I could plug that in back up here. Say 5 minus 10 equals A. So A is equal to negative 5 meters per second squared, which is as we expected because my acceleration was either, scroll up, depending how I looked at it, it was either in the negative x direction here, in this direction, or in the negative y direction here. So it's negative in both cases, as it should be, because it should be the same. All right? A lot of stuff in that, a lot of things to deal with, but it's a lot of vectors, really, dealing with vectors, x and y components, and then applying Newton's second law. Newton's second law is just sum of the forces equals the mass times the acceleration. As you see, it becomes quite complicated. All right? Move on to circular motion. Is that okay? Any questions? Knowing those trig functions will really help you on this. All right, let's do circular motion, then we'll have a little break, okay, about 2. Okay, circular motion just adds a second force or another force to deal with. If I have something that's moving in a circular path, imagine that this is moving in a horizontal path, so I won't consider the gravitational force right now. You know what I'm saying? Like if I'm swinging something over my head, it's moving in a horizontal path. I have a force that's actually causing this to move. So the velocity here, let's say, is in this direction. And let's say that it has a constant speed. So it's moving around in a circular path with a constant speed. But it actually is accelerating because the velocity, while the magnitude isn't changing, is changing what? The direction is constantly changing. So that means that it has to have a constant acceleration. And we call that acceleration the centripetal acceleration. Centripetal acceleration, that centripetal acceleration Sometimes you'll see it as AR for radial, meaning that it's directed radially inwards. Sometimes you'll see it as AC for centripetal, and it's equal to V squared over R. That is the speed squared divided by the radius of the motion from here to here, that distance. We can also apply Newton's second law, and the centripetal force, which I'll call FR for radial, is equal just to the mass times the acceleration, which is mv squared over r. So for example, if I have this object swinging around at a certain speed, say that it's swinging around at, I don't know, 10 meters per second, then I can find the tension in the rope, because the tension in this case is providing the centripetal force. And by the way, so the centripetal force isn't a separate force. The centripetal force is provided by something. So what are some instances where the centripetal force is provided by something in rotational motion? So for example, if I have a car going around in a circle, what's providing the centripetal force? The frictional force. If you're in one of those things at the fireman's fair, I don't know if they have this at the fireman's fair, but one of those things that spins around like a centrifuge and you go up against the wall like this, what's providing the centripetal force? So,
Rotational motion around the axle.
no, there's no tension, right? You're not tied to anything. No?
That's called the gravitron.
I know, but that's wrong.
Centripetal force.
Well, it is a centripetal force, but what's providing the centripetal force? Because the centripetal force isn't a separate force. It's provided by some physical thing. So, the what? Right. The what force is that? The what? Yeah, the normal force. Right. So that's the normal force. The wall is actually pushing it back. It causes you to go in this circular path. Because if the wall wasn't there, what happened? Flying off to the side. Right? So in this case, the centripetal force is provided by the string. So let's say I have a velocity of 10 meters per second. The length of the string is 1 meter. And I want to know, and then the mass of the block is 2 kilograms. If I want to know just what is the tension in the string, that's going to be mv squared over r. It's going to be 2 kilograms times 10 squared over 1. 10 meters per second squared over 1 meter. So that's 2 times 100 or 200 newtons. We did a number of these problems in 101, like with the car going around the corner, finding out what its speed is. In that case, it's the frictional force, but this is just a simple problem. Let's look at a clicker problem. Let's see. Let's look at 205, problem number 205. We'll just do a few questions and we'll take a little break. Looking right here. We are doing animate this. All right, so a few more seconds. Still missing somebody out there. Stop at 120. There you go. Okay, good job. Hey, good job. Did I tell you the nose joke? Did I tell that one too? Yeah, so, see, how's it go? Shoot. What? Did she just tell it?
Go ahead and tell it.
Why is a nose never 12 inches? Because then it'd be a foot. Did I say that one last time? I'm sorry, I don't have anything else for you. Sorry. Usually I have like a sheet with all my jokes on it, but I don't have that for this class. We don't have time for such frivolity in this class. All right, let's see. Let's do a couple more. Shoot. Where am I? Let's just do 206, okay? Try 206 there. 206, I'm sorry. Right, I'll stop at say 140, or when I get number 18 in there. There we go. I'm gonna stop. Okay, B must be right. Go with the majority. So this is simple, right? It's just mv squared over r. If I want to know the acceleration equals not mv squared over r, but v squared over r. Is that what y'all did? If you got it wrong? Yeah, it's just v squared over r because it's just looking for the acceleration. If you're looking for the force, you'd multiply times the mass. So it's 10 squared, 10 meters per second squared over the radius, which is 5, which is v. Did I mark v right? Is that what y'all answered? Yeah, okay. All right, let's take another look at a longer question. See, this is in your book. Let me just double check practice test 2. Y'all okay doing one more question before we have a break? This is practice test 2, number 68. So going to practice test 2, number 68. There's a whole series of questions about kinematics and Newton's laws. That looks like chemistry. Let's come back to this. Let's take a little break right now. I'm sorry. We'll take a little break and then we'll come back to it, okay? So I have 158. Let's come back here at 208. Can we do that? Just 10 minutes?
Yes.
No, according to this, 210. So we'll start back at 210. Oh, and I know y'all got drinks on the veranda and stuff, but y'all can sort of keep it down there just so you're taking a test. Okay, if you want to have drinks on the veranda, have them in here, not out there. Okay? Good. You have 10 minutes. All right. Or go around that corner and talk, right? Yeah. Oh, let me pull it up with me. One in the back of your book, which is, what page is that? Page GS19 if you're following along. Just practice this one. So let's look at this passage. And then that other problem that I pulled up, after we do energy and stuff, we'll come back to it. Because I have a lot of questions on a lot of different topics. So let's try this one, number 26. The following system includes a frictionless pulley. I'll leave you to read it. Let me zoom in a little bit. I scratched it. I had some notes that I'd written in there. I scratched them out for you. Oh. 26. Remember, we worked a similar problem to this earlier, right? Where you have these two bodies and you can write out the forces on them.
Is this similar to the one from 101 when you had the girl dangling something off a cliff?
Mm-hmm. And most of you have the wrong answer as of now. The ones with the correct answers are staying quiet. They're very quiet. There are only a couple who got the correct answer. Oh, now you still have the wrong answer. I think the net force on that 200 Newton block is what? The net force on it is what? It's not moving. Right, 0. The net force is 0. It's not accelerating. All right, just a few more seconds. Yeah, that's not really helping. All right, I'll stop at 2:45. How do we get 19 people? Oh, right. Okay. B is the right answer. So look, I have forces acting here. I have the tension force. I have the weight here. So I know just from looking at this, if it's not accelerating, that the tension has to equal the weight, which is 10 newtons, right? And then up here, I have the tension, I have the weight, I have the normal force. Those aren't relevant because it's not moving in the y direction. And then I have the static frictional force over here. And I know that if it's not moving, the static frictional force has to equal the tension. So it's 10 newtons, which is the same as the weight of the little clock. Okay? Right. We're going to come back to some. We're going to go on into momentum and energy, and then we'll come back to some other practice problems for that will include some inclined planes and stuff with long passages and then several questions about that. And on the test, which isn't next week, right? It's the following week, the test for this class. You'll have some long passages like that, like will work, and is in the practice test. But then you'll also have some questions that are similar to the ones we've been doing, where it's just standalone questions. And on the MCAT, you have that. Like you have long passages, and then you just have problems that are on their own. All right? Well, I see an inclined plane are these type Newton's laws problems. So you need to make sure that you're on board with it. Y'all are on board with them? Let's move on. We'll come back and do some pulley systems later. We'll work some problems. Let's go ahead on to translational and rotational and complex motion. This is on page 26 if you're following along in the book. So just to give you a rundown of circular motion, we had several things that were relevant in circular motion. First of all those kinematics equations now apply for circular motion. Remember we had these sort of, translations that we did. Wherever we had x, or linear displacement, we turned that into an angle theta. Wherever we had v, we turn it into omega, which is the angular velocity. This is angular velocity, we'll say in radians per second. Theta is in radians. That's the SI unit for an angular measurement. Wherever we had acceleration, do y'all remember what it became? Okay, yeah, v squared over r, that's the radial acceleration, or the centripetal acceleration. But when I'm talking about an angular acceleration, it's alpha, which is in radians per second squared. And then wherever we had force, we put in torque, which is in Newton meters. And then when I do these, I can translate my linear equations. I have x, or I had where I had x before, I can say theta equals theta naught plus omega naught t plus 1/2 alpha t squared. These are just the kinematics equations, but now we're expressing them in a circular frame, so something moving in a circular pattern. Let's see, I also have omega equals omega naught plus alpha t. And what's that other one? It was like omega squared equals omega naught squared plus, was it 2 alpha? This might help me out. Theta. Is that right? V squared equals V naught squared plus 2ax. Y'all aren't going to help me out, are you? I don't usually use this, so is that right? Okay, yeah. So this is the excuse me. This is the circular analog to that, if you will. And then also where before we had F equals ma, we're now going to have torque, which is our analog to torque, is equal to what we call the moment of inertia times alpha. This is called the moment of inertia. We'll come back to that in a bit. Whereas before we had F equals ma, and the mass is the inertia. Now we have the moment of inertia, which is similar to the inertia. It describes how difficult is it to get this thing to move into a rotational, into rotation. All right. Your book actually calls torque L for some reason. I don't know why it does that, but if you're following along in your book, this torque is actually called L, which I don't like that at all, because L actually we'll use for something else later. Okay, so let's just call it tau. Can y'all do that? If, it doesn't look like many of you are following along in your book, but if you are, just remember where the book says L, we'll use tau, the Greek letter tau, for torque. Torque is also equal to F times R. This is like I like to think of this as like a radial force. It's like a force applied at some lever arm. So for example, if I have, a seesaw or whatever, if I'm applying a force here, say 2 newtons, at a distance from the center of 1 meter, then I get a torque equal to 2 times 1. That's F times R, which is 2 newtons times 1 meter. All right? So these are 2 different ways to come up with the torque, and this would be equal to 2 Newton meters. You see torques like in a torque wrench. You ever used a torque wrench before? Okay, a torque wrench. Yeah. So a torque wrench has the units on it. What is it usually in units on a torque wrench? Y'all haven't really used a torque wrench, have you? Okay, it's usually in foot-pounds, right? That's a torque. It's a measurement of a force times a distance. That's the measurement of the force times the length of the moment arm. Or it's sometimes in Newton meters on some torque wrenches. All right. When we have equilibrium, there are quite a few problems here on equilibrium, and we'll work through a few. Equilibrium, before, when we were dealing with equilibrium or static problems, we said that the sum of the forces equals 0. And here, instead of saying that, we're just going to say that the sum of the torques equals 0. So if I have 0 torques acting on a body, it shouldn't be rotating. So let's just do a simple one, and then we'll do some slightly more complicated ones. Let's say that I have a seesaw. We did a problem like this, and there are some in the practice test. And I have, my little girl sitting on one end. Where am I going to sit? Am I going to sit here, here, or here if I want to balance out the seesaw? I want to sit in the middle, right? If you have kids, right, if you seesaw with them, it's a lot easier if you sit towards the middle. So I'm going to sit right here to try to balance it out. And if this is, say, 1 meter, and this is, say, 2 meters, and let's say that my little girl has a weight of, 200 newtons, then what force must be applied here in order to balance it? So what must this force be? It has to be 400 newtons, right? So 400 newtons. So I could say that the sum of the torques equals 0. Let me show you how we get that mathematically. That is the torque on this side minus the torque on this side has to equal 0. So that would be F times 1 meter minus 200 newtons times 2 meters equals 0. That's just our condition for equilibrium, right? And so that's going to be F is equal to 400 over 1, or 400 newtons. Let's just do a simple problem. There are some in the handouts that I sent to y'all. Let me see here. Let's look at number 302. Am I going too fast, guys? Skipped over a lot of questions that we could have done for inclined planes. Are y'all okay moving on? You sure? Okay. Number 302. Let's try this one. you want to consider the mass of the board. Don't forget the mass of the board, which is located at what point? The center of gravity, which for a 1 meter board is where? It's at a half a meter. All right, about a few more seconds. So get your answers in. All right. Okay, so here I want to show that my torques are balanced, and I want to figure out what must be the mass of that block in order to get my torques balanced. So I need to recognize that I'm rotating about this point, and that I have another force that is acting right here at a distance of 0.2 meters. Because I can imagine the center of gravity or the center of mass, that all of the mass is acting at a certain point. That point is, in this case, is just at the center of the board. All right, so this force is going to be, it has a mass of 12 kilograms, so that force is going to be 12 times 10, or 120 newtons. All right, and now I want to figure out, well, what is this force over here? So I have F times 0.3 should equal 120 times 0.2. All right, just balancing out the torques. All right, the torque on the left-hand side has to equal the torque on the right-hand side. You know, in class we did this whole thing clockwise, counterclockwise business, but I'm not sure that that's terribly useful for you to do. Just you want to balance the torque. So all the torques in one direction, you must equal the torques in the other direction. So here I can solve this for F. It's going to be, what, 120 times 0.2, what's that, 24, divided by 0.3. That is going to be, what, 80 newtons. Right. And but 80 newtons is 8 kilograms. That's pretty good. So C is the right answer. Yeah, Michaela? Right, it still works out. That's because the G's actually cancel out. So that's fine if you want to do it that way. In fact, I think when you and y'all did this lab with the meter sticks, I think that's what y'all did, that y'all just left the G's out. All right? That sounds like a song. Let the G out. Like a rap song or something. All right? Okay, let's just introduce moment of inertia. And then I'll do a quick Newton's second law problem. So remember, inertia, when we were talking about Newton's first law, it described like how difficult is it to get something to move. So something with a lot of inertia was very difficult to get to move because it has a lot of mass, right? But when we're talking about the moment of inertia, we're asking the question, how difficult is it to get something to rotate? And that's not just a matter of its mass, but it's also a matter of how the mass is distributed. Because if I have something with all of its mass at very small radii, it's going to rotate very easily and can rotate very fast. But if I have something with mass located at big radii, then it's not going to rotate very easily. Is that intuitive to you? Well, that idea comes about in the moments of inertia. And in the class in 101, we spent a lot of time just calculating the moment of inertia for a variety of objects. But in general, the moment of inertia, which we call I, and again, this is sort of our rotational equivalent of mass. So mass measures a linear inertia, but that's not really an appropriate term. It measures inertia of an object in a translational sense, moving in a straight line, and the moment of inertia measures the inertia of something moving in a circular way. So this is equal to the sum of mr squared. And in class, we did this thing where we have, this object, say 1 kilogram at 1 meter, and it had a certain moment of inertia that was equal to 1 kilogram times 1 meter squared. And then if you add a 2 kilogram mass at 2 meters, that's going to add up our moment of inertia. So in this case, it would be 1 kilogram times 1 meter squared plus 2 kilograms times 2 meters squared. And that's equal to 1 plus 4, which is 5 kilogram meters squared. All right. There are a whole host of equations to find the moments of inertia for different bodies. I can't imagine. I haven't seen this actually in the practice test, but nobody's taken it, have they? Taken the MCAT? You've taken it, Evan? Oh, Rory, you've taken it? Do you remember any moment of inertia problems? No. I can't imagine they'd make you memorize those equations. I haven't seen that anywhere, but it would probably be given to you. Like, for example, we did all those problems like with the rotating disk. Let's work through one of those quickly. And this would be a Newton's second law problem for rotation. So let's say that I have a disk. It's rotating about this axis. It has a certain radius. Let's say that that radius is 1 meter. No, let's call it 2 meters. Let's say that the mass of the disk is 10 kilograms. And I'm applying a force. I apply a force to this object that's equal to 5 newtons. And I just want to know how quickly is it accelerating in the rotational direction? Or how quickly is it rotating? What is its angular acceleration? All right, so I know from Newton's second law that torque is equal to I times alpha. It's my Newton's second law in a rotational frame. My torque is equal to F times R, so that's equal to I times alpha. I'm going to tell you that the moment of inertia for a disk is 1/2 mr squared. 1/2 times the mass times the radius squared. So that's 20 kilogram meters squared. All right, that's the moment of inertia of a disk. And now I want to find alpha. It's going to be FR over I. F is going to be, FR, which is 5 newtons times 2 meters. Divided by I, which is, in this case, 20. Because that's what I calculate over here. That's my moment of inertia of this disk. So that's 10 over 20, which is 0.5 radians per second squared. So that is my my angular acceleration. And then from that, you can do all the things that we did with kinematics. So we have those kinematics equations that are now written for this rotational frame with our thetas and our omegas and our alphas, and we can do that here. So say, for example, I want to know what is theta equal to after, I don't know, t equal 2 seconds. I want to know how many revolutions or how many radians has it gone through in that amount of time. Then I can just say theta is equal to omega naught t plus 1/2 alpha t squared 0 times t, assuming it starts at rest, plus 1/2 of 0.5 times t squared, which is 2 seconds squared. It's 1/2 of 4, 2, that's 1 radian. All right? Y'all know how to convert from radians to revolutions and all that jazz? When you're converting, you want to remember that 1 revolution is equal to 360 degrees is equal to 2 pi radians. And so you could conceivably ask, you know, I have this in radians, which is always going to be the SI unit for the angle, but you could also be asked, what is it in degrees or revolutions or whatever. So you need to know that conversion factor. I think most of you know this, right? Okay. So that's sort of a Newton's second law problem. All right, let's look at momentum and collisions. Is this too fast for y'all? There's a lot of material to cover. We only have like 8 hours to do it in, so or 12 hours. So, all right. Y'all can look a little happier for being here. All right. I know this is hard, but let's just keep going. We might come back and do some other example problems about inclined planes and stuff. But let's go on and see momentum, and then we'll address energy. Hold on just a second. Give me just a second. Yeah. All right, so momentum. We had a couple topics that were related to this. We're looking, yeah, Mary.
If we don't have time to go back to our example problems, could you post it like you do for videos for physics 101?
Like solutions to the problems?
Like working them out, just kind of show us a few more.
Mm-hmm. I could do that, yeah. I understand that we could really use some more problems, but I don't want to dwell on one topic for too long. Yeah, but I can do that. I will work on it. I'll get it. I'll try to get you some up, okay? Hold on just a second. All right. So momentum, a couple topics, okay? First of all, when we're talking about linear momentum, and I'll address angular momentum in just a second, but linear momentum, we call the variable p. It's equal to mass times velocity. Scalar or vector, do y'all recall? It's a vector, right? So it's a vector. The linear momentum is a vector quantity. That means that if something has negative and something has positive momentum, they're going to add up as a vector, so they would cancel out. All right, so the linear momentum is just the product of the mass and the velocity. The force is actually equal to the change in the momentum over the time. This was actually how Newton posed his second law. So really, we don't get to Newton's second law until we get into momentum, because this is how he posed it. You see how this looks like Newton's second law, maybe? Well, if you write this out, it's equal to mass times the change in velocity over the change in time. But notice, look, this is acceleration. So this is really just a restating of Newton's second law. This quantity, P, we call the impulse. It's just the change in momentum. So the impulse, which I'll call I here also, is equal to F times T. That is where the impulse I is equal to delta P. Sometimes you see it as I, sometimes you see it as delta P. Okay, but the change in momentum is the impulse, and it's equal to the product of the force times the time. All right, so that's sort of one big class of problems regarding momentum, and we'll look at some of these in a bit. The other big class of problems are conservation of momentum problems, collisions. In all collisions, any collision there is, momentum is conserved. And that just says that the initial momentum equals the final momentum. And this is really useful because if I have two objects that are colliding, say I have a 1 kilogram ball going at 2 meters per second, and then there is a 2 kilogram ball here traveling with a 0 velocity. If the 2 kilogram ball goes away with a velocity equal to 1 meter per second, then I can calculate what should be the velocity of the 1 kilogram ball. All right, so this is the initial state. This is the final state. What should be the velocity of the 1 kilogram ball after the 2 kilogram ball goes away with 1 meter per second? If my initial is equal to my final momentum, here my initial momentum is equal to the mass times velocity. That's 1 times 2 meters per second. So that's 2 kilogram meters per second. Over here, the total momentum has to be the same. So the sum of these two momenta have to add up to equal the same amount. So what must be the velocity of the 1 kilogram mass? It has to be 0, right? So my velocity here has to be 0, because then my total final momentum would be 1 kilogram times 0 meters per second, plus 2 kilograms times 1 meter per second. All right, which would give me the same momentum as what I have up here. The initial momentum has to equal the final momentum. That's conservation of momentum. Now, in collisions, we have two types of collisions. In both types, you conserve momentum, but they're a little bit different, so I want to just tell you in words what they are. First of all, we have elastic, and then we have inelastic collisions. In an elastic collision, I just forgot what elastic. What does elastic mean? You conserve momentum and energy, right? Yes. All right. So yeah, we conserve momentum. And we conserve energy. What are some examples of elastic collisions? There's really only one good example of an elastic collision. Elastic collision is like the collision between gas particles. All right. The reason gas particles are other charged particles because they don't require what when gas particles collide? They don't touch. Right? They don't touch one another because there are field forces that are acting on them. Or when you have two charged particles, like gas particles, they come close to one another. They never actually touch, but they bounce off of one another without touching. So they conserve energy because they're not losing energy by touching one another through friction. Right? In inelastic collisions, they conserve only momentum. All right, only momentum. In all collisions, we conserve momentum, but only in elastic collisions do we conserve energy. Sometimes you can approximate some collisions as elastic, like for example, billiard balls colliding. Often people will say that those are elastic collisions, but they're not true elastic collisions. On these conservation momentums, let me just show you one more thing. It is also true that when we're in 2D, that the initial momentum in the x direction has to equal the final momentum in the x direction. Also, the initial momentum in the y direction has to equal the final momentum in the y direction. So if I have a collision where I have one object that is traveling at a certain angle, and then I have another object that is traveling in another direction, then notice that we have vectors here, because this object actually has momenta, that one momentum vector is in that direction, and one momentum vector is in that direction. This is going to be px. Px would equal to the mass times the x component of the velocity. That would be v cosine theta. And this would be py, which equal to the mass times the velocity times sine of theta. All right, what would be py for this particle? It's going to be 0 because it has no velocity in the y direction. All right, so these things also hold true, that the momentum before and after the collision are held the same. Let's try a problem. This is in the exam crackers business, number 392 that I sent you. So let me pull that up. Here I have a 2D collision. I have these two balls that are going to collide, and I see that one of them is an angle of 60 degrees below the x-axis. And I ask if they stick together after colliding, what is the final horizontal velocity? So what is the velocity in the x direction? All right, so let's try this. They're going to stick together, and I want to know what is the final horizontal velocity. What you want to do here is you're looking for the horizontal velocity, so you really only need to consider the momentum in the x direction. So you'll need to find the x component of that 10 meters per second, and then find the momentum in the x direction, find this momentum in the x direction, add them up, and then ask yourself, well, if I combine these two masses that stick together, what has to be their velocity in order to have the same momentum? If you finish this one, we're going to do number 400. So if you've printed them out, you can look at 400 next. Just a little bit longer, okay? All right. Did we miss somebody? You clicked in, Roy? Okay, good.
Oh,
Huh?
no.
That's okay, I understand. I'm not offended. All right, here we go. Did I ever tell you all my thing about this? I always feel like whenever I get answers like this, I ever tell you?
No, there should be.
No, don't be offended, but I always feel like y'all are giving me the finger. All right, let's see, that must be right. So let's see. Um, so I want to find the momentum in the x direction initially has to equal the momentum in the x direction final. So this problem actually isn't that terrible, right? I can just say the mass times the velocity in the x direction for the first particle plus the mass times the velocity in the x direction for the second particle, that has to equal to the two masses combined times the velocity in the x direction final. All right, so that's going to be 5 kilograms times, what is it, 10 cosine of 60? What's that? Oh, it's a half. All right, so 5 times a half, excuse me, 10 times a half plus the mass, which is 20 kilograms, times negative 10. Just go ahead and figure out what this is, and then I'll go elsewhere to write this. So this is 5 times 10 times a half. That's 25 minus, so am I doing this right? Yeah, it's minus 200. So that's equal to negative 175. So that is my momentum in the x direction. That's in kilogram meters per second. Now I know that when the two balls stick together, they have to have that same momentum. So the px final, which has to equal that, is going to be the sum of the two, which is going to be 20 plus 5 times the velocity final. And so I just do, this has to equal negative 175, divide both sides by 25. That's negative 7 meters per second to the left. It's negative, so that's to the left. All right? Good. Momentum problems are pretty straightforward for the most part. These conservation of momentum problems like this. You just want to set the initial momentum equal to the final momentum. All right, good job. All right, this type of collision actually is, remember, what is the type of collision that only momentum is conserved? Elastic or inelastic? Inelastic. When they stick together, that's called a perfectly inelastic. All right, and so that's a pretty common type of problem when you have two objects that stick together and then they move off at the same velocity. They're actually easier than most conservation momentum problems because in the end you're only finding one velocity, and so you just have fewer unknowns. They're not going off at separate velocities. All right, let's now look at energy and conservation of energy, and then we'll work some more problems. So a couple different things that are going to come up. Oh, what's going on? Yeah, let's just go over this, and then we'll cover a few topics, and we'll take a little break. I know that some of you just want to sit through, but I really need a break if y'all are okay with that. You okay? All right. Okay. Energy. We have a couple different types of energy that we deal with. There are lots of different types, but really the only ones you need to consider are kinetic energy. If you recall, that's 1/2 mv squared. We measured it in joules, the unit. We also have potential energy. In particular, gravitational potential energy is mgh. Again, this is gravitational potential energy. And then we also have elastic potential energy, which is 1/2 kx squared. This is elastic potential energy. All right, kinetic energy is the energy of motion. So if something's moving, it has energy just by the very nature that it's moving. And potential energy is energy that is due to an object's position. So for example here, is due to an object's position within the gravitational field. The higher you go up from the Earth, the more potential it has for motion, because if you let it go, it's going to fall down and it's going to gain kinetic energy. This is elastic potential energy, which is due to what? Like springs? Yeah, okay, so it's due to springs. So if I pull a spring back, it will gain energy just because of the way that I'm pulling up the spring. So the spring has energy contained within it. All right. Big thing that comes up with energy is the conservation of energy, and we'll look at some problems after the break. We had a whole chapter on these in 101. But the conservation of energy just says that E initial is equal to E final. So for example, if I have an object on an inclined plane like this, let's say that it's 5 meters high, I have 2 kilogram mass, and I want to know what is its velocity down here. I can just say that the energy at the top, which is all potential energy, is going to equal the energy at the bottom, which is all going to be kinetic energy. So I would say that the potential energy at the top, which is mgh, is going to equal the kinetic energy at the bottom, which is 1/2 mv squared. At the top, it's not moving, so it has no kinetic energy. At the bottom, it's down at h equals 0, so it has no potential energy. Notice here that the masses cancel. If I want to solve for the velocity, it's going to be the root of 2gh, which in this case, I had a height of 5 meters, so it's going to be 2 times 10 times 5, the root of 50, which is approximately equal to 7 meters per second. All right, we'll see a problem in a bit, like a long passage where it has some problems like this. Another thing that comes up in this is the idea of work. Work is also measured in joules. And in fact, the work energy theorem says that if I do work on an object, I change its energy by that same amount. Right? So if I do work on an object, I change the energy of an object, and we'll see that later in a sample problem. The work is equal to the product of the force times the displacement. If my force and displacement are in opposite directions, I have negative work. This leads to negative work. If my force and displacement are in the same direction, this gives me positive work. So friction then usually has what? Positive or negative work? Usually has what? Negative, because friction almost always opposes the direction of motion, so F and D would be opposite, so it'd have negative work. All right, so we'll see that come up again soon. And one last thing, and that is power, which is just definitions here. Power is equal to energy over time. It just tells you how quickly do you use up energy or how quickly do you gain energy. It's measured in watts. 1 watt is equal to 1 joule per second. Okay? One more thing, and then we'll just round out this 2 o'clock or 3 o'clock. Conservative versus non-conservative forces, which I've seen come up in a few sample problems. Conservative forces they conserve energy. All right, they conserve energy. That's why they're called conservative. Anytime you talk about something being conservative in physics, that usually means it's conserving energy. Conservative forces that conserve energy, there aren't that many. There are really only 2. What are those 2 conservative forces? Remember? One of them is the gravitational force, because it doesn't require contact between 2 objects. Anytime you have contact, you're losing energy. Anybody remember the other one? The magnetic or the electromagnetic force. We just lump those together. So these include the gravitational force and the electric force. right? The gravitational and the electric force. Non-conservative forces don't conserve energy. Don't conserve energy. Big common example is friction. All right, that friction will actually do work on an object that will slow it down, actually cause it to lose energy. All right, this energy is lost to heat, for example. All right, let's take a little break. We'll come back at 3:10. All right, 3:10, and we'll start off with some problems when we come back. I'm going to be asking you in a little bit to give me some comments about the course, so please be thinking about that in the meantime.
Do the exam practice have solutions and like they kind of go through the explanation of it?
Not real involved solutions, like this is mine, but I ripped it out of the binding. So it has the multiple choices, and then in the back, it has very like one sentence descriptions of the solution. But I mean, you can usually figure it out. The solution is pretty detailed. It's detailed enough to figure out how to work it, but it doesn't give step-by-step solutions. I think it's a good book. You might require it in the future. Or,
Well, I was gonna say, whenever I took it, the physical science section, the 3 physics questions that I had were like, one of them was like a sonar wave cancer passage, where like they give you a passage in like a diagram, and they shoot a sonar into like a person's body, and they give you like the amount of time and like what kind of frequency and wavelengths they use.
right.
We're gonna get to that next. Yeah, to determine like where the mass was in their body by the information they gave, like answer other confidential questions on that. And then the first question on the test, I remember was refraction, but it wasn't like regular refraction. It was like the ones that we were just getting to in the physics, like compound, like frame put together, and like magnified refraction. And the other ones are mirrors.
Okay. I hope we'll get to light. I'm not sure. We're not going as quickly as I hope. But do we go faster? Yeah, maybe. Okay. We'll see what we can do. All right. Let's try this. Okay, we can do that. All right. Let's try this one. Okay. So looking at number 68. I have a truck here. It's transporting a load of goods. Oh, it's not read it. Number 68. Oh, this, by the way, this is practice test 2 in your book. It's back in the back of your book, practice test 2. Uh, 5,000. Yeah. Mm-hmm. 5,000. If you finish 68 and you have your book open, you can go on. We're going to look at number 69 and maybe 72. It's on GS 219 in your book. 15 more seconds or so. Just keep it 3 minutes. Let's see, that must be right. So here, the tricky part of this is you want to find out what is the actual height that he's changed. It says that he's traveled up 5 meters, but that's this distance. But really, I want to know what this distance is. Did y'all do that to find the answer? Okay. So this angle is theta, is 30 degrees. And so to find h is going to equal 5 sine of 30. Sine of 30 is a half, so it's going to be 2.5 meters. And then I want to know the potential energy that it's gained. It's just going to be m times g times h. You have to consider both the mass of the truck and the mass of the goods, because they're both going up, so that's going to be 6,000. Yeah, Evan? What now? Okay, all right. So 6,000 times 9.8, which is, we'll just call it 10, make it easier, times the height, which is 2.5. So that's 60,000 times 2.5, which is 120. The closest answer that we have is about 150,000, which is C. That's correct. Okay? Y'all good on that? That's what I put, right? Isn't that what y'all put? Yeah. Okay, let's look also at number, let's do a couple of these. This is a nice problem because it sort of combines several different things. Right? So look at these graphs. You don't have your books. Okay. That's okay. Just look at these graphs. We'll go back, look at the, we want to know what do the velocity versus time graphs look like for this. So I want you to read this, and then I'll go back and show you the graphs, and you can pick the one that you want. So I want to know, what does the velocity versus time graph look like for this truck? It accelerates from an initial velocity of 14 meters per second uniformly. He then ascends the incline at a constant velocity, and then he uniformly decelerates. What does that velocity versus time graph look like? Oh, it's on page GS219. Practice test 2, page 19. All right. So which of these is it? Y'all remember what it says? Want me to go back up? Okay. So let me, I know you can't see it. All right, let's go back down. So which of these is the plot that give the velocity versus time? All right, that's about 5 more seconds. Looks like we got everybody in. Okay, C is right. Very good. You should be able to look at physical situations and be able to represent the velocity and or the displacement versus time. let's move on to fluids. Okay. I'll try to work through some of these problems like you were asking, Mary, and just post those on YouTube. Because I've selected out a number of problems, and we can work those online, so y'all can look at offline if you like. Okay, so that brings together basically 2/3 of the first semester course. So been through kinematics, Newton's laws, circular motion, sort of energy, momentum. Now we're going to move on into fluids. I want to really spend some time on things that we didn't cover in 101. So we'll dwell a little bit longer on sound and oscillations and what have you. And then also hopefully on nuclear physics, if we can get to it in the end. So when we're talking about fluids, we have a number of definitions that we just need to know. One is for the density of an object. The density, which is rho, is just mass over volume. It's measured in kilograms per cubic meter or grams per cubic centimeter. We also talk about the specific gravity of an object. I think this is probably more used in chemistry. Specific gravity. And the specific gravity is equal to the density of the substance divided by the density of water. All right, and the density of water, of course, is 1 gram per cubic centimeter. Actually, the gram or the kilogram used to be based on the definition, or the kilogram, the standard for the kilogram used to be based on the mass of water, so that's why it's equal to 1. And this is equivalent to 1,000 kilograms per cubic meter. All right, so if you had a cubic meter of water, a big cube of water about like this, it would weigh about 1,000, or have a mass of 1,000 kilograms. Now, when we're talking about pressure, I have several things that come up here. Just pressure in general. Excuse me. The pressure due to a column of liquid above you, and then also the buoyant force. So the pressure is defined as the force per unit area, and this is in newtons per square meter. So if I apply a force of 10 newtons over an area of 2 meters squared, then I'm going to have a pressure equal to 5 newtons per meter squared. All right, this is also measured in pascals, so 1 pascal is equal to 1 newton per meter squared. If I have an object, or if I have a fluid, whether it be a liquid or a gas, if I'm a certain distance below the depth of the fluid, say a depth h, then the pressure at that bottom point is equal to rho times g times h, where this is the density of the fluid. And remember, when I say fluid, I mean anything that flows. So fluid involves both liquids and gases. So this applies to both liquids and gases. G, of course, is the acceleration due to gravity, and this is just the depth of the fluid. This comes about from imagining that I have this column of liquid that sits above that point, and this pressure just arises from the weight of that fluid. So when I talk about atmospheric pressure, it's a similar thing. So 1 atmosphere, which is the pressure at sea level, is pretty big. It's like 1 times 10 to the 5th newtons per square meter. And I don't know if y'all recall, remember the little newspaper thing where you lay the newspaper out and you put a pencil underneath it and you do the karate chop? Yeah, that's because of atmospheric pressure. I can't do it here because I don't have newspaper, but you can put like a pencil underneath newspaper and lay it flat, and the weight of the atmosphere will actually hold the pencil, and then you can chop it off with your hand. No? You don't remember. You remember her. Right, because she's a good student. No, you're all good students. Huh?
Surely you followed that balloon filled with hydrogen in the classroom.
Oh, so anyway, when we're walking around outside, it's like we have this big column of air that goes all the way up to the edge of the atmosphere. And that weight is what gives us the atmospheric pressure. And that comes about from this expression, that the atmospheric pressure is just equal to the density of the fluid and the acceleration due to gravity. So this is like our weight sort of times the height. All right, so that's our pressure at a certain depth. And then we also need to consider the buoyant force. So if I have an object of a certain volume, as a volume V, there's a certain buoyant force acting on it. Whether it's floating or submerged all the way down, there is a buoyant force acting up on it, and that buoyant force is equal to the weight of the displaced fluid. This is called Archimedes' principle. Right, Archimedes' principle, the weight of the displaced fluid, and it's equal to the mass of the displaced fluid times g, just by Newton's second law. And the mass of the displaced fluid is equal to the density of the displaced fluid times the volume of the object. So see, this is just based on our definition of density. Density is mass over volume. So mass then is density times volume times g. All right, and so that gives me my buoyant force, which is rho vg. This buoyant force is always equal to this, whatever my object is. Sometimes, however, you can have different situations. Like say, for example, my object is only halfway submerged. If my object has a volume V, then my buoyant force is going to be the density of the fluid, which in this case would be water or whatever it is that's displacing, times the volume of the object divided by 2, or whatever fraction of the object is submerged, times g. Okay? Y'all with me on this? All right, so that's buoyant force. This is always also called Archimedes' principle. Okay. Let's look at this class is wearing me out. Is it wearing y'all out too? Yeah. But it's good. We're fighting the good fight, right? And I have a big crew of doctors. That's how I feel. Okay. What? You can what? Yeah, really. I don't think I could do the organic. That would kill me. Or the gen chem. Both of those would kill me. All right, let's look at fluids in motion. There are a couple different equations. The continuity equation, as well as the Bernoulli's equation, which let's not write that just yet. First of all, when we talk about fluids flowing, we talk about a flow rate. I think your book actually calls it something different. What do they call it? They call it the rate of streamline flow. We'll just call it a flow rate. Flow rate, I'm going to call Q, which is sort of the standard. They call it R. But this is just equal to the change in volume over the change in time. If you're following along in your book, they call it the rate of streamline flow. What that means is that you have no turbulence, so the fluid is just flowing along steady, without changing velocity, without any rotation, without changing its density or any of those other things. So just an ideal fluid flowing along in a pipe, like water flowing in a pipe. This rate of flow is a volume over time. And with ideal fluids, that is fluids that are just flowing straight without any rotation, without any changes in velocity or density, this volume rate will always be the same. So Q will remain constant. for an ideal fluid. All right, so a couple things come out of this. First is the continuity equation. It's also sometimes called the flow rate equation, because the continuity equation says that if your flow rate at one point is equal to some value, then it has to equal the same value at another point. So if I have a pipe and I have a certain flow rate right here, Q1, that is a certain volume of fluid that's passing a point in a given amount of time, then I have to have that same flow rate over here, Q2, right? That's also true if you change the shape of the pipe. So if I have a pipe that looks like this and then it gets bigger, I have a certain flow rate here, Q1. I also have to have that flow rate here, Q2, right? So these the flow rate is going to remain constant, but your velocity is actually going to change. And that comes about with the continuity equation. And it says that the flow rate is equal to the area, the cross-sectional area, which is just the area of this circle, times the velocity. Okay, remember, and so then I can say that since Q1 is equal to Q2, I can say A1V1 equals A2V2. So if my area goes down, what's going to happen to my velocity? It's going to increase. So a good example of this, you have a garden hose, right? You put your finger over the top. What does it do? It comes out faster, so the velocity increases. This is called the continuity equation. You can also see it elsewhere, like if I have multiple pipes coming together, or let's say that I have a river that splits into two pieces. I have a certain flow rate here, Q1, and then I have a flow rate here, Q2 and Q3. This would say that Q1 has to equal Q2 plus Q3, or A1V1 equals A2V2 plus A3V3. With me? All right. Let's see if I pull any questions. I don't have any with this. All right, so that's the continuity equation. The next big equation in fluid flow is called Bernoulli's equation. Bernoulli's equation is based on the conservation of energy. Based on the conservation of energy. And it just says if our fluid has a certain amount of energy at some point within the flow, it has to have that same amount of energy all the way throughout. So it says roughly that the potential energy at one point plus the kinetic energy at one point plus the work being done by the fluid at one point has to equal the same throughout. So it would say this is equal at points 1 and point 2. But the Bernoulli's equation actually looks at not the energy, but usually when we're dealing with fluids, we look at the something per unit volume. So it would divide all three of these by volume. And then we would get something that looks like this. We would get, remember PE is like MGH, and MGH over volume. What's M over V? Density. So I get rho times G times H plus 1/2 rho V squared. See, because this replaces my mass over volume, plus force over area. You can think about this in terms of force times displacement over volume. If you just look at it dimensionally, one of these distances cancels out with one there and just leaves me meters squared. So it's force per unit area, but force over area is just equal to pressure. So this is by Bernoulli's equation. It just says that this has to equal a constant value. And really the big implication out of this is that if my velocity increases, then my pressure will decrease. So since this is a constant value, if the velocity goes up, the pressure goes down. We talked about this a little bit in 101. For example, like if you have an artery and it gets partially blocked, by the continuity equation, the blood is going to go faster within this blockage part, but what's going to happen to the pressure there? It's going to decrease. The systemic pressure will increase. That's something different. That goes back to something we call the Poiseuille equation. I always sound French when I say that. The Poiseuille equation. Like I can pronounce the Poiseuille, but then the equation sounds like I'm trying to fake French. But anyway, the systemic pressure increases overall. So like your blood pressure goes up, but the localized pressure here, because of our Bernoulli's equation, because of this conservation of energy, the pressure is going to decrease. The velocity here increases because of the continuity equation. I'm closing off the area, like putting my finger over the artery, but the velocity increases, but that causes a decrease in pressure. So if you get this too bad, it can actually cause this whole thing to collapse, and then you won't get any blood flow at all. So that would be very, very bad. Okay? I didn't actually have any questions for this, but these were continuity equation and the and Bernoulli's equation. Let's see here. Is there no manometers in this? No, I've seen some manometer problems. They don't cover it here, but I've seen them in the practice problems. So let's go back. All right, so if I have a force, or rather my pressure is equal to rho GH. Remember, this is just the pressure due to a certain height, the fluid. I had this before. I have this fluid, I have a certain depth down here. This is a certain H. My pressure there is equal to rho GH. But if I have a pressure pushing down outside of the fluid, like I have the atmospheric pressure, that's going to be P naught. That's going to add to this. All right? It's like, I don't know, if I'm standing on the scale and I'm reading my weight, and then somebody comes on and they push on my shoulder, I'm going to read a bigger weight, right? That's a similar thing here. If I have a certain pressure down in that point due to the fluid on top of it, but then I have the weight of the atmosphere pushing down on top of it, then I'm going to have an increased pressure. All right, so this is my pressure. This is sort of an addition to the one that we had previously written. Now we can use this to measure pressures, say in a manometer, which looks like this. A manometer has two open tubes filled with a fluid. And you're comparing one pressure to another pressure. I have one pressure pushing down here. I'll call this P. And then I have a known pressure over here, which I'll call P naught. And then I can compare P to P naught based on the difference between these heights. So I'll call this H. And so P is going to equal P naught plus or minus rho GH. In this case, is P bigger or smaller than P naught? It's bigger because it's pushing it down more on this side and pushing this fluid up into the tube. So P is bigger than P naught, and so the appropriate sign that we'd use here would be the positive. So we'd say P would equal to P naught plus rho GH. That's called a manometer. It's used for pressure measurements. Let's do a few questions, okay? We do a few applications questions to this. We're going to look at the exam crackers. We'll do several things. Let's do 541 and 542. I haven't talked about gauge pressure versus absolute pressure. Listen, guys, if you measure your pressure in your tire, it reads like 35 psi or whatever, right? But what if you let all the air out of your tire? What does your gauge read? If you have a flat tire and you put your gauge on there, what does it read? 0, right. That's your gauge pressure. But is your pressure in your tire really 0 pascals or 0 newtons per square meter? No, it's not. It's because it's also the atmosphere. So your gauge pressure does not include the atmosphere. But the absolute pressure is going to be whatever your gauge pressure is plus whatever your atmospheric pressure is. Y'all follow what I'm saying? Your absolute pressure is always bigger than the gauge pressure by the amount of whatever your atmospheric pressure is. All right? Let's, yeah.
So like get something at the bottom of like a beaker of water, you want to say like what the pressure was on that object, what the gauge pressure would be, the pressure of the water,
Right.
and atmospheric pressure, and the gauge pressure to make it absolute pressure.
Right. And the absolute, or the atmospheric pressure, I don't think I gave you all this value, but 1 atmosphere is equal to 100,000 newtons per square meter. That's the weight of the atmosphere that sits above your head. Let's do number 541. Here I'm looking for the gauge pressure. So that's just going to be the pressure due to the height of the liquid. If you finish, just go ahead and do 542 as well. All right, maybe 15 more seconds or so. Stop at 2:30. One more person up there. All right, so here, my pressure is just equal to rho times G times H. Remember, the density of water, which is just a number you should probably know, is 1,000 kilograms per cubic meter. G is 10 meters per second squared. That's just our acceleration due to gravity. And now, what is our depth? So he's in 30 meters. They give a lot of information here that you don't really need. He was at 20 meters above the bottom, so he was at 10 meters. And then he goes down to 10 meters above the bottom. So now he's what depth below the fluid? He's 20 meters. So that's the value that we need. I don't know why they give you all that other stuff, just to confuse you, I guess. All right, so that's 1,000 times 10, which is 20,000. Or excuse me, it's 10,000 times 20, which is 200,000. So that's going to be B is the right answer. What answer is that? 541. Yeah, B is the right answer. Okay, let's try this next one now too. Now, what is the absolute pressure here? here he's actually 20 meters above the bottom. What is the absolute pressure? About 15 more seconds. Stop at 1 minute. Okay, C is right. So here we need to include the atmospheric pressure. So at 20 meters, it's going to be P equals rho GH plus P naught. All right, that's including that because it's asking for absolute pressure there. That's going to be 1,000 times 10 times the depth. He's 20 meters above the bottom, so that means that he's 10 meters from the top, which is really what we want, plus 1 times 10 to the fifth, which is 100,000. 1, 2, 3, 4. This is 1 times 10 to the fifth as well, so it's going to be C is the right answer. All right, absolute versus gauge pressure. Let's do a couple more. Let's do this 547. It's referring to this figure right here. I have this figure where you have 4 different liquids, and I want to know where's the pressure the greatest. Where's the fluid pressure the greatest? This is P1, this is P2, and this is P3. 547, where's the pressure the greatest? Oh yeah, I'm sorry. We'll wrap up soon, just a few minutes. Where is the pressure the greatest? Also notice that you have this little cavity here. It's just filled with air. It's like a, I don't know. A is P1, B is P2, C is P3. About 15 more seconds. All right. Okay. What P1? Looks like we were split between P1 and P2. The answer is P2. The reason is that P1 just sits below this amount of fluid, right? And so that's what contributing to the pressure. P2, however, sits under this amount of fluid plus whatever this is, this amount of air, plus this additional amount of fluid. Right? So P2 has a bit more pressure than P1. And then P3 is in between the two. So P2 is the greatest. All right. What did y'all put? A? Oh, I know what you were thinking. I can see that. Yeah. You might have been thinking that, well, that was sort of my fault, that you have this cavity here, and it's absorbing the pressure due to this topmost part. Is that what you were thinking? Yeah, that's not the case, though. That's not what's happening here. I mean, if it were like a rigid cavity, that would be the case. I'm sorry, I misled you on that. But that's not the case here.
How will we know if it'd be like soft or rigid?
Well, let's read the problem. So, I don't know. It doesn't say. It's like an air bubble or something, yeah. Anthony? It would be the most dense. Mm-hmm. Yeah, it would be the most dense. I have to think about that. There might be more to that than just what I'm saying. All right. Why don't we stop. But I do want you to take out a sheet of paper, and don't put your name on it, but I just want you to sort of tell me what you would change about the course, if anything. All right, I really appreciate any feedback, because if we can change stuff, this is the time to do it, because we're already, halfway through the course. So just take a few minutes. You don't need to put your name on it. And just lay it up here, and then y'all can go. And remember, no exam next week. We'll do the exam when we come back on Friday. I was glad to see all of y'all. I went downstairs, and the department head's like, "Oh, so you probably have no class at all, huh?" I'm like, "No, they're all there, as far as I can tell. I think you're all here." So I'm glad for that. Y'all are good students. You don't have to thank me. It's my job, but I just want y'all to benefit from it. So. No, it is part of my. And I'll try to make some screencasts just of some extra problems. Y'all use those? Yeah, we're not going to be able to reach everything in class. Thank you, Kirby. Have a good break, okay? And if you're in my 102 class, I have your exams if you want to pick those up. But Andrew, sorry, I don't have yours, okay? He's in 202. Yeah. We'll get to some topics next week that we didn't get to in the class. So sound. Maybe a little bit of what do I have here? Mary, Allison, who's in the online class? Is that just you, Mary? Anybody else? Yeah, it's online. Thank you, Anthony. Have a good weekend.
We'll watch your house for you.
We have a house sitter. I appreciate that. If y'all want, I'll put the solution on the screen, so I'll try to get you over the break. Really? There we go. Did I give you your speaker? There's yours. No, that's Mary's. I guess you got out of it. Take it later.
Mary, do you want to put your back? Yes, I'm not right now. Thanks so much for
You need yours?
I tried knocking last night. And
When I go in?
Yeah.
Oh God, what time?
I think it was like 2.
I was telling
Yeah, I know, yeah, place, please, you know, it's okay. She's like, oh yeah, Megan, she's like, things were in here, or later. And I was like, I think they're safe, I'm gonna answer, so I'm not always bothering.
Make sure I put like that in my head.
Yeah,
What's the
I
name
know,
of that?
same thing. She was like, and she's like,
Yeah, I know what you're
and she's like, very concerned.
I don't know where it is.
Okay.
But you know
With
what?
me for the night, like I didn't even see my name.
Thank you.
Right.
Okay.
I'm sorry.
Bye.
Bye.
Really? Like,
I'm sorry. I'm very sorry. I don't.
she probably took it just to psych you out to make you feel bad.
Right. Because that's really what she wants.
Probably. Like, she probably wants you to feel bad all of Mardi Gras vacation that you lost the schedule.
Right. What is that thing?
So what was the average grade in the
It's like 78. It's pretty decent, actually.
Have a good break.
Y'all too. I'll see you Friday. Oh yeah, I'll see you Thursday. Yeah, so we had this for 2 more weeks. And, yeah, that's it. Oh yeah. Heather, I'll get the solutions up soon to that exam. I know you're anxious to see them.
Wait, great.
To see it.
Yeah, thank you.
I wanted to ask you, I know you were busy, but, how long did you have to wait before you got your NCAT results? So it's about a month, 3 or 4 weeks, and that's about average?
Right, yeah. They tell you online. It's like,
Okay, I didn't see that, but that's good to know.
they'll mail it to you, and they'll also put it online, and they'll official that email you whenever it shows up online.
And as soon as you get your results, you can.
Actually, you can go online and see whatever date you took the test. They tell you exactly what day or what like range of days it's supposed to come out.
Oh,
And it
okay.
usually comes out like 2:30 in the afternoon every time.
Okay, and then as soon as you get your results, you can decide if you sit again.
Right.
So there's no like wait period. You just basically have to wait.
You can take whenever you want, whenever it's offered, as many times as you want.
Right.
But the medical school's probably gonna look at your most recent score.
They look at your most recent score and they don't average them or?
No,
No.
it's your most recent score.
Okay.
Really, you can't choose what